first thing we're going to talk about is the anatomy of a proof. Okay. So has anybody ever seen proofs before?
Maybe.
All right. There's lots of different types of proofs. In this class, we will do what's called a 2-column proof. There's also paragraph proofs where you like write it as an essay. We're not doing that because I'm not grading that. And then there's flow chart proofs where you kind of write it horizontally instead of vertically. We don't really do much of that either. So we're going to stick with 2-column proofs. It's called a 2-column proof because there are 2 columns, right? The first column is the statements column. This is where you are making conclusions about what happens next in the problem. This is kind of like your if-thens, right? You start with something and they're like, oh, well, if this is true, then I can make this conclusion. And then you piggyback off of that. Well, then if this is true, then I can say this. And if this is true, then I can say this. And so it's a whole series of if-then conclusion statements, basically, right, that you are concluding on your own. Then the second column is the reasons column. It's also known as the justification column. This is where you have to justify every single minute step of math work that you have written down in your statements column. Okay, this is why I told you guys in Unit 1 to start training your brains. As soon as you write something down, ask yourself what allows you to do that, because that's what's preparing us for this. Okay, the only things that you are allowed to put in the reasons column are definitions, postulates, properties, and or theorems. There are some other wiggle room ones that we'll talk about today, but that's pretty much it. Stuff that you would see in bold or in a box in a textbook, that's what you get to put in the reasons column. Okay? All right. Almost every geometric proof will have a diagram, right? It'll have some pictures of, angles, rays, segments, all that good stuff that we did in Unit 1. This is what I want to talk about right here. What also comes along with a proof is a given statement and a proof statement. How many of you guys have ever done a scavenger hunt before? All right. What's the first thing? How does every scavenger hunt start? With a clue, right? With a piece of paper. Yes, with a clue on it, right? You're given a clue and you read the clue and you're like, ooh, where does this take me? And then you go to that place, right? And then you get another clue from that spot and it leads you somewhere else. That is what a proof is, okay? I want you to think of the proofs as like little scavenger hunts or puzzles, right? If you think about it from that perspective, they're actually kind of fun. I promise. So the given statement, is your first clue because you have to have somewhere to start. So it's like your first little breadcrumb, your first little hint that tells you where to start the problem from. Okay. Then once you have your given, then you have your prove statement. This is the goal. You're not done with the problem until you prove what the prove statement is telling you to prove. Okay? So you get a starting clue, and then you have to work your way and figure out how you deductively reason your way to the proof. Okay? Little puzzles. Yay! So excited. All right. Before we actually get to our first proof, we have to learn a few things because really basic proofs start off with properties. So we need to learn our properties. And before you ask, yes, you must memorize all of these properties and their names and what they mean. Okay? Everything we learn in here, you have to remember. I promise by the end of class today, you're going to have all of these already memorized. Okay? The more you use it, the more your brain is just going to burn into your brain.
I don't know if I like them.
You will, I promise. We're going to use them so often today, you're going to have them all down before you leave, I promise.
Yeah, that's why I might not like it.
All right. Now, in Algebra 1, or even pre-algebra, I don't know if your teacher did this, but in Algebra 1, you use almost all of these properties of equality. Maybe not the yellow highlighted ones, which we'll talk about a little bit, but all the ones that aren't highlighted, you use them on a daily basis in Algebra 1. Your teacher just may not have referred to them before, okay? So here we go. The first 4 properties, addition, subtraction, multiplication, and division property. We use these on a daily basis in math. These are the properties that allow us to solve equations, okay? So I'm just going to talk about the addition property just really quick. The addition property basically says if A equals B, then A plus C equals B plus C, meaning if I add the exact same number to the left and the right-hand side of an equation, I can still claim that they are equal. And again, you do this every day. For example, what if I wanted you to solve the equation x minus 3 equals 5? What do we do to solve this equation? You add 3 to both sides. And that cancels, but lo and behold, we still state that the two sides are equal to each other. And what allows us to do this is the addition property, right? Oh, I added 3 to both sides, but my statement is still equal because I kept the equation balanced. That's the addition property. If I subtracted 3 from both sides, that would be the subtraction property. The multiplication property, I'm just going to write some quick examples here. The multiplication property might look like this. X divided by 3 equals 2. What am I going to do to both sides to solve this? I'm going to multiply by 3 on both sides, and because I've kept it balanced, my equation is still equal. That is the multiplication property. Whenever you do something to both sides of an equation to solve. Yeah? Yeah. Okay, and the division property, of course, you would divide both sides. Like if I had 2x equals 4, I would divide by 2. I just use the division property. Okay, so those are not new to us. All right, now we get to these highlighted ones. They're highlighted for a reason. We'll talk more about it here in a few minutes. Here we go. The reflexive property. The reflexive property sounds really weird right now because we're not actually going to use it until unit 3. Okay? The reflexive property basically says anything is equal to itself. 5 equals 5. Yeah, sure. Right? Negative 8 equals negative 8. Sure. From a geometry perspective, we might say the measure of angle A equals the measure of angle A. Right? And you're thinking, why would I ever need to use this? You won't for a while, but you need to know that property. Okay, the reflexive property of equality. I remember it because reflexive kind of sounds like reflective, like I'm looking in a mirror. So it's just like a mirror image of itself. Kind of how I remember that. All right. Symmetric property of equality. Symmetric property of equality says if A equals B, then B equals A. So basically, if I took an equation and I switched to the left and the right side, it'd still be the exact same equation. Okay, symmetric property of equality. Let me show you when you would use this. Mostly. There's lots of reasons, but this is going to be the most popular way. All right, so let's say I asked you to solve the equation. 5 equals x plus 2. Well, what property am I going to use to solve this?
The subtraction.
The subtraction property, right? I would use the subtraction property to subtract 2 from both sides, right? And that's going to give me 3 equals x. Now, how many of you guys naturally, which I'm assuming most of y'all, how many of you guys naturally, instead of writing 3 equals x and boxing that as your answer, how many of y'all write that as x equals 3? Most of us do, right? Because we love the x on the left-hand side. It just looks nicer and it reads better, right? But in proofs, you're not allowed to just intuitively do that. In a proof, if you want to switch the x from the right-hand side to the left-hand side, you can. But what am I going to have to use to do that? Which property are we talking about right now? The symmetric property of equality. I'm just going to abbreviate that to you. So that's typically where we're going to see the symmetric property of equality. When the x is on the right-hand side the entire way down, but for some reason they want me to prove it where it's on the left, so I have to switch it at the last minute. Okay.
I was just gonna ask, like, when we do that, like really, do we have to write symmetric property?
In a proof, okay. If you're just solving a regular problem for me, no. But if it's in a proof, yes. In a proof, you're not allowed to just hop right to x equals 3. Because the x wasn't on the left-hand side. It was on the right-hand side, and you were asked to switch it and put it on the left. That actually takes a mathematical step. Okay? So remember what I told you guys. Usually the smartest people have the hardest times with proofs because our brains naturally do 2 to 3 or 4 steps at a time because we're good at multitasking different math steps, right? I can add and divide in one step. But in a proof, you can't do that. You're only allowed to do one tiny math process at a time. And for some people, that's really hard, right? Because they're like, oh, well, of course I can go from here to here. but there's like 5 steps in between that you're hopping over, right? And so that's the hard part. Okay. All right. Moving on. The transitive property of equality. All right. The transitive property is one of those. Okay, that makes total sense once you read it. It says if A equals B and B equals C, then I can conclude that A must equal C. And why must that be true? Why does A have to equal C? Because they both equal B, right? If everybody is equal to B, doesn't everybody have to be equal to each other?
Yeah.
Okay, and so that's what the transitive property is saying. I have these two equalities. Well, if they share, and guys, I'm just writing this down because I use this phrase all the time. I tend to use the phrase middleman a lot. Does everyone know what a middleman is?
Yeah.
Okay, like if you're trading cards with somebody and you're like, oh, Bob's gonna give it to Sally and Sally's gonna give it to Joe. Well, at the end of the day, Bob gave it to Joe via Sally, right? She's the middleman, right? That's kind of the same thing here, right? I have a commonality of two things that are shared, so A and C are connected through B,
Like
right?
groceries.
Okay, so I'm gonna use that phrase middleman quite a bit, okay? All right, the substitution property. The substitution property, you guys use this all the time, especially when you check your answers in algebra, right? If I get x equals 3, how can I check my answer? That's right. I know if x equals 3, I should be able to go back to the original problem and substitute a 3 in everywhere I see an x because I've proven they are equal. And if two things are equal, then I can substitute them in for one another. We're going to use that guy a lot.
When you say reflexive, like reflexive or something, or do you have to say reflexive property of equality?
You actually have to say reflexive property of equality. Yeah, it's going to be a lot of writing. I will allow you to abbreviate slightly on some things, like if you want to write prop instead of property. But please, I get this from students all the time. Please don't be lazy. I always have students that are like, oh, well, instead of reflexive property of equality, I'm just going to write RPE. And I'm like, not if you want me to grade it, you're not. Right? Do not abbreviate with like acronyms or whatever. I'm not going to take it. Okay? What? No. Not yet. No. All right. The distributive property. You guys are all, you should be very familiar with the distributive property, right? If I have parentheses with a binomial or more terms inside, I know I can distribute and multiply multiple times and get rid of the parentheses. I had a little problem with that distributive property today. I'm going to talk about it in just a second. The last one is combining like terms. This one is technically not a property at all, but it is a process that you're allowed to put in a proof. If I want to add two like terms together, then you can do that. But it's not really a property because you're not moving anything to the other side to solve it. You're actually simplifying an expression.
I'm allowed
right?
to put in quick line.
If you have to use it, then yes. Yes. So I wanted to put an example of how this might look in our class, right? Because we're going to be doing a lot of algebra equations, but they're going to be about geometric stuff. So here we go. If I told you the measure of angle 1 plus another measure of angle 1 equals 90, then I can then simplify that and write that as two measures of angle 1 because I'm combining the like terms because there's two of them. It's no different than saying x plus x equals 5 and then simplifying that to saying 2x equals 5. I'm just doing it with angles instead of x's. Does that make sense, everybody? Yeah. Yes, you can abbreviate this one CLT for combining like terms. Yeah, that's fine. That's one I'll let you get away with. CLT, or you can write it out. Or if you don't want to write combining like terms, you can actually write the operation of addition. Because all I'm really doing is I'm adding these two things together because they're like terms. So if you just want to write the operation of addition, you can. It would not be the addition property, though. Does everybody understand the difference? The addition property is if I'm solving an equation, I add something to both sides to solve it, right? So that's not what we're doing here. All right, before we move on, I want to add one more thing to the bottom of your notes right here, just into page 1. If I know this is going to look weird because it wouldn't really happen like this, but if I was solving an equation and I ended up with 2 times 3 times 4, if I ended up with x equals 2 times 3 times 4, Well, obviously, I would never leave my answer looking like this. I would write it as what? I would write it as x equals 24, right? But how did I go from here to here?
Fine.
Okay, I just heard 4 different answers. Okay, I'm going to talk about all of them. Okay, I'm going to talk about all of them. Okay, so to go from here to here, is this the multiplication property? No, right? The multiplication property is when I'm solving an equation and I multiply both sides by a denominator to get rid of the fraction to solve the problem. That's the multiplication property. I'm not doing that here, right? I also heard somebody say the distributive property. I've had this issue all day today. Please make sure you understand, I will count it wrong if you write the distributive property here. The distributive property is not the same thing as just multiplying, right? In order to be the, I don't know why I'm using so many air quotes today. In order to be the distributive property, right, it would have to look like this. Like, I have to have like a binomial with a plus sign, hence the need for me to distribute the 2 to multiple terms. Does that make sense to everybody? That's the distributive property. There's not a plus sign to be found here. There's not a binomial anywhere to be found. So I'm not distributing. Okay. So I need to make sure that you know the difference between that. Okay. So aren't all I'm doing is just straight up multiplying? This is just multiplication. Please don't write combining like terms. Combining means to add, right? So multiplying does not fall under that window, right? This would be the operation of multiplying. Because when you just add 2 numbers together or subtract 2 numbers from one another or multiply or divide, that's just basic arithmetic. Those are operations, right? Like the order of operations, right? So if all you're doing is just multiplying 2 numbers together, that's not really a property. It's just an arithmetic operation. Yeah.
What does he have like 12 plus? Actually, wait.
That's right. You just said the word plus, right? Right, and there is no plus sign, right? Combining means to add, right? So if you don't see any plus signs or minus signs, then the combining like terms is off the table. Okay. All right, here we go. We're gonna play a little game. Turn the page. We're gonna play Name That Property. Because if you can't name justified property, then we're gonna be in trouble when we get to our proofs.
I know this.
All right. You okay back there? All right. Now, these statements are written as if-thens, not as proofs. So instead of being written as a 2-column situation, they're just written horizontally. I want to let you know, you don't have to write this down if you don't want to. If this is my statements and my reasons column, basically it's saying, if I was told 4x equals 20, then what allows me, what is the justification I would put right here to know that I could then say x must equal 5? The division property, right? Isn't the only way to get from here to here is to divide both sides by 4? That's the division property. All right, this next one is the hardest one of the day. Here we go. If AB plus EF equals EF plus CD, then AB must equal CD. Yeah, you can look. Yeah. All right, how many of us think it's transitive property of equality?
Let me guess.
Oh.
It is not. Now, this is the, I know I was really tricky with this one. The reason why it's not the transitive property, I'm going to go back and look at it. How many equal signs do you have to see in order to use the transitive property? 3. This equals this, that equals that, so this equals that. You have to have 3 equal signs. We don't have that here.
Is it Sylvester?
So if these were equals, yes. If these were equal signs, like if it was equals and these equal, then that would be the transitive property, but that's not what we're looking at. So this is when you need to ask yourself, I know this looks weird because it's geometry segment in an algebra equation. So I know that's kind of strange, but this is what we're going to be looking at. You have to ask yourself, what did they get rid of to go from this equation to this one? They got rid of the EF on both sides. If I cover up the EF on both sides, doesn't that give me this? So how would I get rid of the same EF from one side to the other? You would subtract it away, right? I know this one was tricky. So if I were to subtract EF from both sides, they would cancel out, and that would give me the conclusion that AB equals CD. Okay? So this is the subtraction property. Please do not abbreviate that sub property because why?
You won't like it.
I will not like it, but why will I not like it? Because there's a substitution property, right? And I would not know which one you were referring to, right? So for now, we're going to write things out. Once we get the hang of it, things, and we'll.
If I drop the ION.
That's what I just said. Because there's a substitution property, right? So that's what we're saying. All right. What about the next one? How can I start with this and then claim 3x? That is the distributive property. I had a parentheses with a binomial inside. Therefore, the only way I'm going to get rid of that is by distributing. Or that's what they did anyway. We could have also divided by 3. Hold on. I was writing division. Distributive property.
I feel like I'm gonna check my notes a lot.
Yes, you should be checking your notes a lot. Yes, while doing your homework. All right. What about starting with this and then claiming that 2x must equal negative 100? They clearly multiplied both sides by 5 to start solving that equation. So that is the multiplication property.
Weird that I want to like look at the property.
Yeah, said to subtract.
No, but that's there's not really a multiplicative property. There's a multiplicative inverse, which is not the same thing. All right.
I see 3 equals.
Me too. But you gotta be careful, guys. The last one. If the measure of angle 1 is 30 and the angle 1 plus angle 2 equals 90, that's a lot of information. Then what would allow me to conclude that I could just write 30 plus angle 2 equals 90? Okay, this is not the transitive property. Not combining like terms. What changed from this equation, 1 plus 2 equals 90, to 30 plus 2 equals 90? What changed? Nope. What? Yes, didn't they replace? Isn't the only difference between this equation and this equation is that they replaced the measure of angle 1 with a 30? Well, didn't they tell me also that angle 1 equals 30? So if two things are equal and I can then replace them for one another, that is the substitution property. Good job. Again, I know these are kind of hard to see sometimes, but once we get the hang of it. Guys, I always tell students that you need at least 20 to 30 proofs under your belt before you start getting really comfortable with proofs. All right, that's usually kind of the average. So be prepared to kind of live in a zone of uncomfortableness for a little while. It's going to be okay, I promise. I've been doing this a long time. All right, here we go. Properties of congruence. There's more, right? All the properties we just discussed were properties of equality, meaning I can only use them with equal signs, right? So there are also properties of congruence, which I can only use with congruent signs, right? So do y'all notice anything about the names of these properties?
Same thing except
That's right. They're the exact same names as the highlighted ones on the previous page. They just say of congruence instead of equality. Okay? So they have literally the exact same meaning, except with congruency symbols. Because remember in Unit 1, we learned there's a difference between equal signs and congruent symbols. One is a numerical basis, and one is just talking about the object. Okay? All right. Williams, guys, are we paying attention? Okay. So here we go. I'm not going to read through all these, but I just gave you some examples of how this would look in a geometry class because that's really the only place you use congruency symbols. So the reflexive property says anything is congruent to itself. Okay. The symmetric property says if AB equals congruent to CD, then CD is congruent to AB, right? I can flip the left-right side. It's the same thing. Transitive property, looking for the middleman, right? Who are they congruent to? So who's congruent to each other? So like right here, everybody's congruent to CD, which means AB and EF must also be congruent to each other. Or I could do the same thing with angles, okay? All right. Sorry, I know I'm going kind of quick. So I'm gonna
Go quicker.
go quicker.
Higher.
Okay. So much important stuff I want to say there today. All right. So you might be wondering why I have these two islands drawn on the next little pink box here underneath the definition of congruence. I need everyone to pay attention to this. This is super important. When you're doing a geometric proof, you're either going to be starting off in the land of equality or you're going to be starting off in the land of congruency. Hence my two islands. I'm going to make this guy, I'm going to put an equal sign there and a congruency sign here. This island is going to be, let's say, the land of equality. It is very obvious, I can talk today. It's super obvious if you're living in the land of equality because all you will see is equal signs. Okay, so it's very easy to tell which land you're living in. And this other island is going to be the land of congruency or just land of congruent. Again, very easy to tell if I'm living in the land of congruence because everything is a congruent symbol. Here's the problem. Sometimes you may have to switch back and forth between the land of equality and the land of congruence or vice versa, which you are allowed to do, but only if you add a step in the proof that tells the reader that you're hopping from one land to the other, okay? And that reason, I'm going to go back and forth, is the definition of congruent, which we learned way back in Unit 1. This is not a new definition for us. If things are congruent, it means they are equal in size, shape, or measure. I'm getting some entertainment. Okay, so anytime you need to switch back and forth, definition of congruent is the way that we do that. If two things are congruent, they're equal. If they're equal, they're congruent, right? So we can use it either way. All right, let's play another little game of name that property. Here we go. Symmetric. Yes. So at this point, it is not enough to just say symmetric property. You must add of congruent. Yes, you can abbreviate it with the congruency symbol. That's okay. The symmetric property of congruence. Why do I have to have the of congruence? Because there's also a symmetric property of equality. And I need to know that you know what land we're living in. Okay? All right, turn the page. What about number 2? This is the transitive property of congruence. Yes. Right? Obviously, angle T is acting as a middleman. Oh, everybody's congruent to angle T. So R and P must be congruent to each other. That's the transitive property of congruence. All right, what about number 3? Segment AB is congruent to segment CD Therefore, the length of AB must equal the length of CD.
Definition of congruent.
Oh, you're so bright. Definition of congruent. This is just what we were talking about with the island. The only difference from this statement to this statement, it looks exactly the same, except one's a congruency statement and one's an equality statement. So I have gone back and forth between the islands there. Definition of congruent.
And I agree.
You can put a congruency symbol instead of congruent, yes, that's okay. All right, what about the last one? It is also definition of congruent, because all I've done is started off in the land of equality, but I've written the exact same thing just in the land of congruency. Nothing has changed other than the land that we're living in. Okay? All right, how are we feeling about properties? Okay, here we go. Let's start some proofs. Here we go. Now, I have a lot to say about proofs today since it's the first day, so bear with me. All right, so the first thing I want to tell you about proofs. Number one, we're baby stepping it. We're going to start with some algebra proofs and not geometric proofs. Some of you guys are going to fall in love with these algebra proofs. You're going to be like, proofs are so easy. We will never do these again after today. This is just a one-day thing. Everything from this point on will be a geometric proof, not an algebra one, okay? So we're just kind of, like I said, baby stepping it. Now, do you guys notice how this proof is partially filled in?
Yeah.
Most students love that. They're like, oh, cool, I've got some context clues. It's halfway done for me. I hate this. I hate when we give students partially filled in proofs. Not to be mean, but because, do you think there's only one way to prove that x equals -1? No. There's lots of different ways I can solve an equation to get x equals -1. So I really hate when we do this for students because proofs are all about your brain and what path your brain decides to take a problem. Do you think your proof has to look like your neighbor's? No, it doesn't have to look like mine. If you look at my answer key, some of you guys are going to be like, I didn't do it that way. Awesome. You didn't have to do your proof the same way I did, right? Because proofs are about free thinking and deductive reasoning, right? Where does my brain lead me, okay? So I hate this because it pigeonholes you, it forces you to follow somebody else's logic, okay? So we're going to do it one time, and basically this is it. All right. So notice the given. The given is just an algebra equation, and we're trying to prove that the solution is x equals -1. So all we're doing is solving an equation, right? My algebra students, I don't have any this semester, but they always hate me because I make my algebra students do this. When they first learn how to solve an equation, I make them do a proof and write the properties down. You can tell I'm so low. But it helps, right, with our deductive reasoning skills.
Multiplication.
All right. So I'm going to highlight my proof statement. I just like to do that because you should always look to your final goal. If I don't know where I'm trying to go, well, then what's the point? All right, here we go. Where in the world did this statement come from? It was the given. And that's exactly what you're going to write in your very first reason box. It will always say given in the first box. Because remember, it's your first clue. Right? This is a scavenger hunt. Here's your first clue. It was given to me. Now I'm going to start finding clues on my own. Okay? Now this person has chosen to solve this particular equation a very particular way. Do you have to do it this way? Well, yes, on this one because it's still given. But so what did they choose to do first?
Multiplication.
They multiplied. The only thing that changed from step 1 to step 2 is they have chosen to multiply both sides by 2. Why would they do this?
To eliminate that.
Yeah, and a lot of people like doing this, right? They don't like working with fractions, so they'll multiply by the common denominator and get rid of them. And of course, what property is that? This is the multiplication property. All right, whenever I multiply this both sides by the same number to solve the equation, that is multiplication. All right, cool. So now I'm at step 2. Now I need to progress in the equation and get to my step 3. Well, what are we going to do to get there? Meaning, yeah, and guys, use your context clues. Doesn't this already tell me over here what I'm going to do next? Right? But we should know that anyway. I shouldn't have to fill that in. We know that when we have parentheses with the binomial inside, we're going to have to distribute the 2's, right, to get rid of the parentheses. All right, so what is that going to give me when I multiply the left side by 2? 8 minus x. Right? If I multiply everybody by 2, I'm going to get 8 minus x equals 7 minus 2x. If I distribute the 2, and you don't normally show your math work in a proof. If you need to, you can go off to the side or whatever. Proofs should be very clean, right? And not like work shown in between the steps or whatever. You're not solving the equation, you're proving the equation, and it's a little bit different. All right. Now again, this person, whoever did this proof, is leading us into a certain place. So what have they done from step 3 to step 4? They clearly subtracted the 7, right? You can tell the x's didn't go anywhere, but the constants all got moved to the left. And they subtracted that 7, so subtraction property. So they got all their constants to the left, right, using the subtraction property. Now what would we do naturally? You would add the x's to the other side, right, because we got all the constants to the left, so we're going to get all of our x's to the right. And if I add that x over, what's that going to give me? 1 equals negative x. And they've already filled that in for you. It is the addition property because I added an x to both sides. Am I losing anybody? Good? Okay. We're not quite done because, of course, when we solve an equation, we got to get x by itself. So how are we going to get that x by itself? We're going to divide by -1 on both sides. Or technically, couldn't I multiply both sides by -1? That would accomplish the same goal. So I'm going to use the division property, but if you wrote multiplication property, it would not be incorrect because multiplying and dividing by -1 would accomplish the same goal. So I would take either one there. Now, why aren't we done? That's right. You're not done until your final line says exactly what the proof statement says. And the proof statement has the x on the left, but we didn't end up that way. So we're going to flip it around. And you're right. That is the symmetric property of equality. I need that because there's also a symmetric property of congruence. And yay, I like to put little smiley faces at the end. A little pat on the back for getting to the proof. Okay. Now, again, we're never going to do these tasks today. You have some of these on your homework tonight. Again, we're just kind of practicing getting that flow of a proof down. All right. All right. Could I have done this proof faster? Yeah. Absolutely. If I didn't distribute and multiply by 2, I could have just gone ahead and moved all the constants to the left and the x's to the right. I could have gotten this done in like 5 steps instead of 7. And that would have been totally awesome, right? Your proof doesn't have to look like your neighbor's, okay? All right. Here's my favorite part. Are we ready? We're going to step it up just a notch. Here we go. Oh, no. We got 4 proofs to go. 4 more proofs. Then we're done. We have so much time. Oh, we're going so fast.
Go fast. I already need to go to bed.
45 minutes. Wait till I think our notes tomorrow are going to take like the full 90, so prepare yourselves. All right. Monday will be faster. All right, are we ready? All right. I'll wait. We're all ready to go. Just have yourself a pencil. All right. So we're still living in the land of algebra here, right? So we're nothing geometric about this whatsoever yet, but we're just going to step up the difficulty just a notch. Okay, here we go. Given, look at all these givens. There's 3 separate givens here. And then they want us to prove that K equals 4R. Okay? Now, before we get to that, I want to talk about a couple of things. The first thing I want to talk about is how we're going to write the given in the proof. Guys, there are 3 different ways you can write your givens in a proof when there's more than one. Obviously, if there's just one, like the last problem, you would just write the given and call it a day. But this one has 3 separate givens. Everybody listening? Okay. Option number 1. You can literally, since they're all given to you, you can literally take all of these and rewrite all of them in that number 1 box and then write given and call it a day. Right? So if you just want to copy all 3 of them and cram them in that box, you totally can. Okay? Option number 2, because there's 3 given, you also have the option to just write them 3 separate times, 1 per box. This is what I am going to do today. You don't have to do that if you don't want to. But I'm going to write all of my givens separately. And the reason why I would suggest you do this, especially at the beginning, once you get the hang of proofs, you can start cramming them all in there if you want to. But I'm going to write them all separately because they all have a purpose. And I don't want them all crammed in the first little box and I have to like sit there and like, piecemeal around the, all that stuff all crammed together. Your third option is to write the givens as you use them. Maybe I only want to use the first 2 givens at first, and I don't need the third given until step 5, right? So you can stagger your givens as needed, okay? So I don't care which of those options you pick, and right now I don't expect you to know what you want to do, but once we get about 15 proofs out under our belts, you'll start figuring out how you want yours to lay out, okay? All right, here we go. Let's talk about how we're going to deductively reason our way through this. So my proof is to get k equal to 4r. Guys, how many different variables are in the given? 4. There's 4 different variables. I've got k's, p's, m's, and r's. So I was given 4 different variables, but I only want to narrow it down to k's and r's. So what variables am I going to have to eliminate somewhere along the way? I'm going to have to get rid of the p's and the m's. I'm going to write that down for myself. You don't have to, but this is just kind of how my brain is going to think through this. Get rid of p's and m's. This is going to happen somewhere along the way, so I'm just left with a statement in terms of k's and r's. Yes, absolutely.
Swap out the P.
Now, I'm going to do my little spiel for a second. Everybody listen, bear with me. My little soapbox on proofs. Okay. Like I said before, some of you guys are going to be awesome at this from the get-go. Some of you guys are going to struggle a little bit. It's all good, right? It doesn't matter where you're at. I've been doing this forever, so I'm pretty good at teaching proofs. The one thing I will say about proofs is you have to be brave enough to start. That's really it. I will literally see students just stare at their paper for like 10 minutes, and I'm like, what's our plan? Like, what are we going to do? And they're like, I don't know. You have to just be brave enough to write something down. Is it always going to be correct? No. Who cares, right? Math is all about trying something and seeing if it works. And if it doesn't, you scrap it, you start over, right? And that's going to happen in proofs. Some of you guys are going to start writing stuff down, and you're going to start getting to like the 10th step, and you're like, I'm no closer to the proof than when I started. And that's your clue to erase and start over and take another path, okay? I've literally seen this proof done like 10 different ways today. And it's awesome, right? Because all of our brains are going to see something different. So you just have to be brave enough to write something down and start. I promise it will lead you somewhere, okay? Here's my other soapbox thing. Everybody ready? Here's what I do not want you to do. Please do not... Sorry, I'm trying to figure out how I just used the word not, and I was going to say not again. Please allow yourself to struggle, right? It is a very uncomfortable place to struggle on a math problem. I totally get that, right? What I don't want you to do is just go look at my answer key and copy all the answers to my proofs, okay? I have students do that every year. And by the first quiz, I know exactly who those people are because they have no idea how to think on their own, okay? You have to allow yourself to struggle. You have to write something down, see where it takes you, and if it's not good, erase it and do something else. You have to allow that to happen, okay? If you need to go look at the answer key and be like, oh, I'm just going to look at the first line and see what Miss Jester did. Okay, look at one line, close it, and then see if that helps you, okay? But you have to struggle. You got to let yourself do it, okay? You're screwing yourself if you don't. You won't be able to do a proof for the next 5 units in this class, and then you won't pass, I promise. Okay, so struggle now, pay off later. Okay, yeah.
like addition or something, do we write it down in that?
No. Well, you're just going to do it on the next step, and then you'll justify what allowed you to do it on the right.
I mean, like, what if you add in one multiply?
You can't do two things in one. You can only do one tiny step at a time. Okay, so here we go. We're trying to get rid of P's and M's. We can start anywhere we want. I see a lot of things that are equal. I see that P is equal to K, and I see M is equal to 4R. Well, what can we do with stuff when we know they're equal? You can substitute them in. If I know P is equal to K, can't I put a P in wherever I see a K? Or a K wherever I see a P? And if M is equal to 4R, then wherever I see an M, I can substitute 4R because they're equal, so I can substitute them in. So that's kind of where we're going in this problem. All right, so what would y'all like to substitute? Keeping them, what? The PK? All right, the PK first, so we're gonna do it that way. You get to do your proof on your own here in just a second. So let's say we're gonna use P equals K. Okay, which variable am I gonna substitute in for what? All right, because we want to get rid of the P's, right? All right, so we want to plug a K in for the P. All right, so if I plug in a K for the P, we're going to get K plus K equals 2M. Not yet. Remember, you can't do too many steps at once. You're right, that's going to be our next one.
Substitution.
And that is the substitution property. Now, this is totally not required. This is totally optional, but sometimes a lot of students like when they do the substitution property, they like to say, okay, I took step number 2 and I inserted it into step number 1, just so they can kind of keep track of where that substitution happened. So if you go back and look at a proof, you're not like having to be like, okay, how do I get that? What did I substitute? Because you gave yourself a little footnote over here. You don't have to do that. That's totally optional. Yes, you can abbreviate it prop. All right, now what should we do? Okay, sure. Again, so many different paths I could take from here. So if you want to combine like terms, we get 2K equals 2M. And yes, that is combining like terms. All I'm doing is adding a K to a K.
K equals M, right?
Yes, I haven't proven that yet, but yes, that's coming.
M equals 4R.
What?
It's like in the proof, it says K equals 4R.
Yeah, but I don't know that. That's what I'm trying to prove. I don't know that K equals 4R yet. You can't use the proof statement to prove this proof statement. You know what I'm saying? Yeah, so we don't know that yet. That's our goal. We're trying to get to that. All right, now what can I do with 2K equals 2M? Can't I divide by 2 on both sides? All right. And again, maybe we're on the right path, maybe we're not. Just trust yourself enough to try it and just see where it goes, okay? And of course, what did I do? What justifies that? This is the division property since I divided by 2 on both sides. And you can put division property of equality if you want, but you don't have to write the of equality because there's no other division property. So that's why I'm not writing that. All right, cool. So now I know K equals M. What am I going to do now? We're going to do another substitution because right here in step 3, we haven't used him yet. I know M equals 4R. So instead of M, I'm going to write 4R. So K equals 4R. And isn't that what we were trying to prove all along? And my reason, of course, for that step, substitution property. And I'm going to put a little footnote for myself. What did we substitute? We substituted step 3 into step 6. Again, you don't have to do that. That's just kind of there if you like that. And notice I didn't even need the 8th step. Just because you see 8 steps doesn't mean you have to use all of them. I'm always going to give you a blank table, right? And sometimes I'm going to give you way more than you need. And sometimes you might kind of take a longer route than I thought you would take. And if you need to add a step 9 and a step 10, feel free to add lines. to the proof if you need it. Okay? All right, let's see how comfortable you guys are with that. I want you guys to do this one by yourself.
The symmetric property of plan twice. And do it twice.
Well, you shouldn't have to do it twice.
So
If you do it
swap it back and
twice,
forth.
yeah. Feel free to talk it out with people at your table if you want to, or try it by yourself and then look at your neighbors and compare, because I guarantee you probably aren't going to do it the same way. Remember, brave enough to start. If it's not correct, who cares? Right? Just use a substitution property and plug something in for something and just see where it takes you. Well, no. The problem is your givens, all of these are your givens. You can't write this. This was not given to you. These are your givens, and these have to be the first things that you write in your proof, because these are your starting clues. They go in the first line. You see what I'm saying? You just kept them over here, and then you just wrote like step number 2 over here. But you can't do that. Because you wrote given, but was this given to you? No. You use these clues to then assume that this is also true. You see what I'm saying? Okay.
No, so I this one, but
right now I would keep them separate like I did up there. So that if you want to just shove all of them into the first thing, you totally can. And then what you did was you substituted the P in for the K, or the K in for the P, and you substituted the 4R in. And I'm actually okay with that because you're using the substitution property. But you did 2 substitutions in one, but because it's the same property, I'm fine with that. So, K equals 8R, K, yes, and then you divide it, yes. You just gotta scooch all that down, because your givens have to be in your program.
right?
Are we being brave, trying? Find a substitution. It doesn't matter. You have to trust it, right? You gotta trust that it's going to work itself out somewhere in the middle of the problem, but you might not see it until step 6, and that's kind of why you can just trust it. So just do a substitution and see where it takes you. I did it. Yeah.
Where did 6A equals?
I had it in equal 1/3 B. If I multiply those by 3, and I did 3A. I multiplied both by 6, and I did 6A.
Okay, so. Okay, so 6A, no, I see where I was not going to justify. So you multiply this by 6 to get this. Okay, and then. Oh, so because 6A is, okay, and you put a C, okay. Okay, so this is where you lost it, because you're doing steps in your head that you haven't justified on the paper. You know what I'm saying? So if you are plugging in 1/2, okay. I'm trying to think about it. If you want to, you would have to completely erase this line, and you would have to multiply both of these by 2 and write 2B equals D.
Because you're taking this step and doubling it, and then you would have the two be in common, then you could say C. Right. But you're doing a little too much in your head. You just have to make sure that you're writing all those down. Does that make sense? I will say that you are the only one I've seen today that do it that way. But it totally works. Does it work out?
I'm a genius. I forgot what they called that.
No.
I did it like a.
What did we do from here to here? What did you substitute to get from here to
I
here?
did a substitution.
So make sure, do you notice how your order is not the same as mine? But you're actually fine because you're right, since the 6A does equal C, then you should have written it as C. And then you'll be good. No, it's fine, right? You just want to put that. No. If you write them all over the top like that in one swoop, then you're like done writing given. And how did you get that? I don't see that written anywhere. We're going to prove in that. See what I'm saying? You skipped a step. You need to add. You need to show me that you've multiplied that first given by 6 on both sides. Then you can substitute it in. Does that make sense? Are we good? So you added your and then you put this B down your test and then you multiply it. You switch it, so I love it. Yes, because all you're doing is multiplying your numbers together. No, you're fine. I know if you just actually wrote 1/3 instead of 1/3. One of these should be at half, not a third. Alright guys, as I'm looking, I've literally seen at least 6 different ways of people writing this proof. Okay? It's amazing, right? We don't all have to think the same way. Really quick. The one, you guys are doing awesome. The one tiny little criticism I would have is that some of you guys are doing steps in your head
but not writing them down, right? You're like, oh, well, because if I multiply this by 6, I can write this and that'll go in here. And I'm like, well, that's awesome, but you have to write that down, right? You can't do it in your head, right? You have to write it down on the paper, okay? All right. Do you think we can try some geometric proofs now?
So you can control the panel.
It's okay. You can go back and look for it. All right, here we go. Turn the page. This is the most important part. Now we're actually going to do geometric proofs. All right. I did not put any geometric proofs on your homework. Well, there's one that has like a segment on it, but it's mostly just an algebra problem. But everything from this point on is going to be a geometric proof, okay? Here we go. This is like the most basic geometric proof I can possibly give you. It's a very short one. Okay, so the given says AC, I'm going to go ahead and write it as I'm talking. AC equals AB plus AE. That's always the first thing. Please do not, I will totally count off points if you do this. Oh, arrow, arrow. Like, please don't be lazy. I see students do this all the time and like, oh, I'm just going to just write arrows or quotes or whatever. Don't do that. Don't be lazy. All right. Now, most geometric proofs are going to be super obvious. You're going to be like, well, of course that's true, right? They want us to prove that AB equals BC. Well, let's just think about that. There is no congruent signs. You're right. Let's just think about that. AC, so the whole thing, is equal to AB plus AB. So if I take this AB and add another AB to it, it gives me the length of the whole thing. Doesn't that mean these two segments have to be the same length? So intuitively, we already know that that has to be true. But can you prove that it's true? That's the challenge. All right? So when you're doing a geometric proof, I know it seems super obvious. Well, remember, the given is a clue. The given is a clue for you to use as a jumping off point, right? It's not supposed to be something that necessarily makes sense to you. It's a clue, something that you might not have known on your own just by looking at the picture, okay? All right, so when you're doing a proof, guys, I'm going to tell you, completing a geometric proof is basically a 3-step process. Step number 1, use up everything your given tells you. Now, this given, he doesn't lead me to anything else. He's just a clue all by himself, and he doesn't lead me to anything else. So as soon as I write this given down, I'm done with him. He doesn't lead me to another clue. So when that happens, then you need to go to your diagram and ask yourself, is there something I've learned in class so far that would make sense that I could write about this picture? Does everybody notice I have a line segment that's been split into 2 parts? What did we, well, I don't know it's a midpoint yet. No. What did we learn in Unit 1 that says, oh, I've got a segment that's broken up in 2 parts, and these 2 parts added together must equal the whole thing? Which addition postulate? The segment addition postulate. Remember, guys, you can't forget everything from Unit 1. We're going to use everything all year long, right? So when I look at this diagram, it is screaming segment addition postulate when I look at that diagram. And you'll notice that this kind of almost looks like the segment addition postulate. It's just not really, right? That's also kind of my clue that that's where it's wanting me to go. Okay, so what segment addition postulate equation would I write for this picture? I hope we didn't forget everything. AB plus BC equals AC. When I look at this diagram, I'm like, oh yeah, cool. Part plus part equals the whole thing. And I'm allowed to write this because the segment addition postulate told me I could. It doesn't matter which way you write it. The segment addition, this is why I was so crazy about when we were in Unit 1, when you were doing your homework, making yourself justify every equation that you wrote down. This is why. Right? Okay. So Is this diagram telling me anything else? No. Guys, this is the most basic geometric picture we can possibly look at and approve. This diagram is not telling me anything. So I've used up my given. I've used up my diagram. So once you've used up your clues from your given and your diagram, that is when you need to go analyze the steps that you've just written in your proof and see if there's a connection that can be made between the two things we just wrote down. And what's the connection between this equation and this equation?
AB. AC and AB.
Okay?
AC.
The main thing we want to jump on, aren't both of these expressions equal to AB? I'm sorry, AC?
Yeah.
So I know AB plus AB equals AC, and I know AB plus BC also equals AC. So everybody equals AC. So what does that mean? It is the whatchamacallit. It's the middleman.
Oh no, symmetric.
No, it's not symmetric.
No,
No, because symmetric property says if A equals B, then B equals A. I'm not flipping stuff around.
transitive.
This is the transitive property. I have two things that equal AC, right? All of this equals AC, and all of this also equals AC. So don't these two things have to equal each other? That's the transitive property. I know what you're going to say. Hold on just 1 second. So if they equal AC, then they equal each other. So I'm going to write AB plus AB equals AB plus BC. I can merge lines lines 1 and 2 because they're equal to AC. Okay, Shelby, what we're going to say? Yes. That's what I figured you were going to ask. So this is technically the transitive property of equality. Two things equal the same thing, therefore they must all equal each other. But Shelby just said, could I use the substitution property here? Yes, I would actually take substitution property as well. Please don't write them both. You can pick one. And of course, the reason why is because, well, if this equals AC, then can't I substitute that in place of this AC? And I'm right back to here. So it's two different ways to kind of look at it. Okay, so I would take either answer there. All right. And then, of course, I'm hoping, it sounds like most of you guys are seeing where this is going. Hoping. Notice we're trying to get AB equals BC. So what am I trying to get rid of? I need to get rid of these ABs. But luckily, there's one on each side. So I can subtract them away. If you want to write that in your notes, you can. You would never actually write this in a proof. But if you want to write that underneath, so you're like, how did we get rid of those? And when you look back at your notes, you can, but don't ever put that in the actual proof. You just do that in your head. So I'm going to subtract an AB from each side. And what do you know? AB then must equal BC.
I thought of a weird way to solve.
Was it longer than 4 steps?
Probably.
Sure.
So I was thinking about combining like terms.
Yeah.
Then AC would equal 2B or
2AB.
2AB. And then I would have divided the 1/2 of AC is equal to AB. And then AB plus BC is equal to AC minus AB.
So you totally do that. Is that a lot more steps? Yes. Would that be okay? Yes. I know yes, I know your mind works a little bit differently. Which is totally fine. I love it. All right. Okay. Here we go. Oh, I'm gonna put my little smiley face. Okay. Here we go. Give me one for you guys. Here we go. Last one. Last one. This one's a little more involved. Here we go. B is the midpoint of AC. Oh, hold on. Before we get started, I like to highlight and make sure I look at my proof
We are trying to prove at the end of the day that the length of AB is equal to the length of CD. Now, when you read your givens again, you'll be like, well, of course they are, but you have to prove it. Here we go. My first given, B is the midpoint. I'm going to abbreviate just a little bit, but it has to be enough so somebody knows exactly what I'm still saying. B is the midpoint of AC. Do you guys want to go ahead and write all the givens down, or do you want to use them one at a time? All at the same time? Okay. That's fine. Again, the more we do proofs, the more you'll kind of figure out how you want to do that. All right, so I've gone ahead and written my givens. Now, these are the type of givens that I like. These are the givens that keep on giving because they are clues that lead me to other clues. And the reason why I know that's happening is because this is what I love right here. These are vocabulary words. We love when there is a vocabulary word in one of your givens because your next step is then going to be to use that vocabulary word to tell the reader of your proof what that is implying to be true. Okay, so here we go. I'm going to look at my diagram also. Please mark your diagrams. I'm totally going to count off half the points of your proof if you don't label your diagrams in your proofs. It is so important that your diagrams are labeled that I'm going to be super picky about it. Yes. So my first given was that B is the midpoint of AC. Okay, so B is the midpoint of AC. We learned this in Unit 1. What does it mean to be a midpoint? Okay, it is the average, but what does that mean as far as line segments go?
Oh wait, it's like dissects divide.
Yes, that a midpoint splits a segment into two congruent halves. You can go back and look at the definitions in your Unit 1 notes. So as soon as I read that given, can't I put congruency marks here and here? I know that has to be true because, so here we go. I'm going to go write that in my proof. A segment AB must be congruent to segment BC. I know this must be true because why? Okay, but what do you think I'm going to write in my reasons column? I can't write B as the midpoint. What? Definition of what vocab word did we just use? Midpoint. Whatever the vocabulary word is, you guys, your next line is going to be definition of that vocabulary word because you're literally telling the reader what that means. That's right. And then we're going to do the same thing for our other given. We've used up that given. Now we go to C is the midpoint of BD. Okay. Well, if C is the midpoint of BD, then can't I put a single congruency mark on those as well?
Yeah.
And so what am I going to write in my proof? I know segment BC is congruent to segment CD. And how do I know this? The definition of midpoint. Again, I ran into another vocabulary word. It happened to be the same one. So I know I'm going to need definition of the vocab word. So now we have used up our given. They lead me to no other clues. My diagram is not going to give me any more clues because I've literally already written down all the clues that I've drawn on the diagram. So if I've used up my given, I've used up my diagram, now I'm going to go to what I've just written in my proof and see if there's a connection that can be made. And there is. What are they sharing?
BC.
Yes. Oh my goodness. Everybody's congruent to BC. It literally is the middleman in my diagram because it's the middle segment that they're sharing. Right? But this is how that looks in a proof. I can't stand when that makes little weird parallelograms. All right, let me get back to this one button. There we go. I'm going to kind of, there we go. So if everybody's congruent to BC, then what can I write on my next step?
Substitution.
What do I, no, what's my next statement going to be?
that AB must be congruent to CD. Now, what's my reason for that? Okay. I'm going to write transitive property of congruence. Okay. Now, could I have also, I heard some of y'all say substitution property. Would that have, does that fly here?
No, because it's congruent.
That's right. On this one, I cannot use the substitution property because the substitution property is an equality property. He only exists in the land of equality. So up here on this proof, it was either or because I was in the land of equality, so either one would apply. But on this one, I'm in the land of congruency, so I cannot use the substitution property. It has to be transitive property. I heard some of y'all saying symmetric property. Guys, symmetric property is only, it would only look like this. If this said AB is congruent to CD, and then on the next line, I wrote CD is congruent to AB. That's the symmetric property. When I take a line and then I choose to flip it on the next line. Does that make sense? That's not what's happening here. All right, and we're not done because they wanted us to end up in the land of equality, not the land of congruency. I have everything I need. It's in the right order and all that good stuff, but I'm just going to convert it into the land of equality. And my reason for being able to do that? Definition of congruent. These are our little palm trees, right? We're going back and forth between the land of congruency and equality, and the only reason for that is the definition of congruent that allows me to do that. Yes, it doesn't matter if you're going from equality to congruent or congruent to equality. Woo, how do we feel about all that? I know about sorry, it's important. Paragraph has to be like complete sentences.
Are we gonna work problems like this?
What?
We're gonna get problems like this where we have to write
Word problem.
like it gives us all this stuff in a paragraph.
All right, I know a lot of you guys already grabbed your homework. Who still needs that homework assigned? Anybody else need a I'm so sorry that took so long. You still have 5 minutes. You can probably get the first page done before you leave.
I'll do it. We'll take a question.
Did we stretch the brain today? Sorry. Remember, yeah, there's only 4 minutes left. Oh.